corner and just like play the guitar and like they couldn't get the stuff. It was like,
So funny.
I'm gonna work problem
So
number
passionate about
7
it.
from assignment
oh, that
8-5?
was the last one that I did.
8-5. Let me try that one.
Yeah, I guess she's got.
I'm not.
And so the problem in my web work has a 5 to the n times n factorial divided by n to the n. And it's going to go from 1 to infinity. The question is converge or diverge and explain. So when you see the factorial, the products, the n powers, it just screams for you to do the ratio test. So we're going to look at the limit as n goes to infinity. The test looks at the limit as n goes to infinity of the an plus first term over the an term. And we're going to look at the size of the limit. Limit smaller than 1 means it converges. A limit bigger than 1 means it diverges. A limit equals to 1 would be trouble for us here because this is the perfect test for this series. So I'm going to go through there and rewrite the general terms where each n is replaced by n plus 1. So I have 5 raised to the n plus 1 power. Then I have n plus 1 factorial. On the bottom, we're going to have an n plus 1 as the base n and n plus 1 as the power. When we divide by an, we'll flip that around and multiply it. So I'll put the n to the n here, 5 to the n here, and factorial. And then what we typically do is write that n plus 1 factorial as n plus 1 times n factorial. And then we take the exponents that are sums and write them as the product of the bases. So I'm going to write the 5 to the n plus 1 is 5 to the n times 5 to the 1. N plus 1 factorial is n plus 1 times n factorial. N plus 1 to the n plus 1 is n plus 1 to the n, and then n plus 1 to the 1. And then I have my 5 to the n, n factorial, n to the n. So when I write it like that, I can see that the n factorials cancel. 5 to the n cancels, and I also have an extra factor of n plus 1. Let me mark those out in red. That one cancels with that one. N factorial cancels here. N plus 1 cancels there. And what we're left to evaluate is the limit as n goes to infinity. I have 5 times n to the n over n plus 1 to the n.
You get 5
Why is that 5?
because of tower power.
I got infinity over infinity.
Oh, yeah, never mind. I was thinking.
Let me write it like this. 5 itself, we don't care about. Let me put the 5 there. Can I do that? Can I do that step right there?
Isn't this like a known series?
You know it?
No, but
And that's the
I
answer.
recognize it.
And the answer is no, I don't know it either.
You did the end test or?
Well, I can't start changing tests in the middle of my
Oh, yeah, you
test.
can.
Natural law.
We're gonna use a logarithm. Okay, so here's where I may have messed up with doing the log step. So here we go. No, I don't think I think I'm okay. I think I can hold this 5 to the end. And then find this using logarithms and then put the 5 onto our answer. So I'm gonna say, let this part here be equal to L. Okay, where L is equal to the limit as n goes to infinity of n over n plus 1 to the n. So inside the parentheses, what's happening to n over n plus 1? As n goes to infinity. Just inside.
1.
That's 1, right? So I have 1 to the infinity, which is one of our indeterminate forms that we've seen before, that we can get rid of that indeterminate form by using a logarithm. So I'll take the natural log of both sides.
Does the 5 have to stay in for that natural log?
Well, I didn't. I'm gonna call my limit 5 times L.
Shouldn't be 1/5 though. Oh.
Why? I just
Oh, okay, I
Pulled
see,
it
I see, I
here.
see.
called that part
I get you.
L. So I'm gonna take the natural log here, which pulls the n down in front. And then I have the natural log of the base. But that looks like infinity times 0. Because the log of 1 is 0. And one trick to get rid of that is to put this in the denominator as a 1 over n. Hopefully gets us in the right form to use L'Hopital's rule. Is it in the right form?
I believe so.
Because the log of 1 is 0 and 1 over infinity becomes 0. So it has the form of 0 over 0, we're going to do L'Hopital's rule. Pull it up and do it in here. The derivative of the natural log of u is 1 over u times u prime. So if I flip this u term over, I get n plus 1 over n. And now I can take the derivative in here with the quotient rule. Bottom times the derivative of the top gives me n plus 1 times 1. Minus the top times the derivative bottom gives me n times 1, all over the bottom squared. And then downstairs, the derivative of 1 over n is negative 1 over n squared. So just inside this box here, I have n plus 1 minus n. So that's just going to simplify to 1 over n plus 1 squared. Right, this numerator simplifies to 1. And then dividing by negative 1 over n squared, I'll put it up here like that.
Get rid of one of the n plus 1s.
Yeah, one of the n plus 1s and one of the n's are gone.
You can also cancel those 1s.
That,
Thank you.
that,
Cancel the 1s.
cancel the 1s, well, one of them's going to give me a negative 1. So it looks like we need to take the limit as n goes to infinity. I'll put the minus sign up on top with that n. And then the n plus 1. So what's that limit?
Negative
1. And you have to multiply like by 5.
By
right?
5.
Right? Not yet. What I called in the box was L.
No, wait,
Right?
Negative
So
1.
now I've got to exponentiate it. Right?
Sorry.
So L is e to the negative 1. So now I put that in there and I get that this is equal to 5 times e to the -1, or 5 divided by e. E is 2.7-ish. So overall, what's the size of that fraction in comparison to 1? It's bigger than 1. So our series diverges.
And that's the ratio test.
That's the ratio test. So I wasn't very careful with that number when we worked it last time. So I'll try to pay more attention to it right now. Long problem. Serpentine little problem.
So are you like, so that 5 being tacked on pretty much changes the divergence of this
It does.
series?
It
So
does.
like, would you recommend us do this kind of process with a number like that just about every single time we encounter it, or would you suggest different?
What if I left it here? If I left it, where would it have been? If I left it here, then I'd have the log of a product. So in here, I would have, I don't know where I would have put it. It would have been here, outside the parentheses. And so I'd have the log of, right? I would have the natural log of 5 times n over n plus 1 to the n, and I can't use that power rule until this is out of the way. So I could write that as the natural log of 5 plus the natural log of that thing and carry the log of 5 around.
Okay.
Okay? But just remember, you can't do the power rule. You can't bring that down while that 5's in the way.
The natural log of 5 is going to clear up whenever you do the other side of the natural log of L.
Right? And all of that you take the limit of. And then this step would have all that in it. So it would show up back in the end when you exponentiate it. You'd have a product of e to the natural log of 5 with e to the natural log of that limit. So danger warning, be careful with runaway constants before you use the log properties. I wasn't. Anything else on web work you'd like to talk about? What about that handout that I asked you to finish? Were there any things on there that you didn't finish, would like to finish, would like to do together? The handout was asking questions about conditional convergence and absolute convergence.
Would it be better to test for conditional or absolute convergence first?
I always like to test for absolute convergence first. Let's kind of look at these. Maybe I should do them all. You want to watch them?
Yep. At least some of them.
Maybe some of them?
We do number 5.
We can do number 5. Camera is. Move over a little bit. So we're back at the series worksheet that we've been working on. Worksheet that won't end. Let me see if you've got these answers. The series worksheet. Number 1, we have this series. 4 to the k divided by 5 to the k. And k goes from 0 to infinity. Which you can also write like this. As 4/5 all to the k. Maybe when you write it like that, you recognize it as a geometric series. When k is 0, my first term is 1. And then it parades on by multiples of 4/5. So this one was a geometric series with r is equal to 4/5. Our conclusion there is whenever the multiplier in absolute value is smaller than 1, then the series converges. Since this series has all positive terms, the convergence is automatically absolute convergence. And to what value? A geometric series converges to S is equal to A over 1 minus R. A was 1, R is 4/5. So S is 1 over 1 minus 4/5. So 1 over 1/5 is 5. Right? Okay, then we give you the same thing as a sequence. As a sequence, that looks the same way. Or look at it that way or that way. But a sequence converges if it has a limit. So we look to take the limit of that.
Yes.
And if your ratio is smaller than 1 in here, when you take subsequent higher and higher powers, that value goes to 0, which is why we came up with this statement up here. So the sequence converges to that number. The series converges to that number. Sequence converges if it has a limit. A series converges if it passes one of our series tests. Number 3, you could do either with an integral test or with a comparison test. So I'll do a comparison test. You can compare it to 4 divided by 5 times k. So the 4 over 5 doesn't matter. You can always factor those out. That behaves like 1 over k. What do you know about that series?
Divergent.
The divergent p series. This has the same numerator, but less in the denominator. So it is bigger. The series we're testing is bigger than a divergent series. And that's the way we need it for the direct comparison test. Bigger than divergent is divergent. So that was number 3. Number 4. How'd you do number 4?
Just took the limit.
Took the limit because it looks very top heavy, doesn't it? Which means my limit's not going to go to 0. That's called the test for divergence.
Do we have an acronym for that?
TFD. Number 4, the limit does not go to 0 since the limit as k goes to infinity of k cubed minus 3k divided by 1 plus the natural log of k, right? Logarithms are real slow. So we got the slow pokes on the bottom and the fast ones on top. It's not equal to 0. The series diverges.
Are you sure that infinity does not equal 0? Maybe you should work it out just to be sure. We'll add all the numbers of infinity.
I'm just stating that in our test for divergence, if the limit is other than 0, the series diverges. Anything other than 0, including infinity.
Yeah, but infinity is just 2 zeros.
It's a double 0.
It's the Siamese twins of zeros.
It's a 0 with a weird belt.
Infinity is just 0,
Ooh.
0, which is 0.
They write
Infinity is
top
gonna be
to
a number
bottom
in integral bound, so
Is it?
I'm gonna.
You should go for pi if you can.
That would be awesome.
So it's actually.
We'll put them together and go infinity to the pi.
all those like pi, tau,
Yeah, pi.
infinity,
You should
e,
throw an I in there.
Yeah, I like your
in,
imaginary player.
imaginary.
I promise he's not on the court, guys. He doesn't really exist.
That would be wonderful.
Okay, so number
Call it five.
5.
Don't know how to
K is
do
equal to
this.
1 to infinity of k minus 1 over k times 2 to the k plus 9. As soon as I have adding and subtracting, I always think in terms of maybe try some sort of comparison test. So I just throw away the 1 and the 9 and choose BK, my comparison series, to be that series without the adding and subtracting. And then those k's would cancel. So my BK just is 1 over 2 to the k. What kind of series is that?
That's geometric.
It's a geometric series. R is 1/2. So it's a convergent geometric series.
I did that with the whichever RCT it is, I don't know. I just wrote,
RCT.
like, I'm trying to
Comparison
either
test.
ratio or. the
Ratio
other one.
comparison
The
test.
limit comparison test.
Racial
I don't get a limit comparison test.
The racial comparison test, Jackson.
Limit
Really?
comparison test says we take the limit
You're the one who said it.
as k goes to infinity of the given series over the comparison series.
It worked.
And if we get a positive finite limit, they both do the same thing.
And it's from RCT right there. Okay.
So when I divide by that, I put the 2 to the k up here. And so they both behave of the order of k times 2 to the k as being the highest power.
I think the limit is 1/10, but I don't know.
Why 1/10? Why not just 1?
I don't know. I got 1/10 somehow.
General ratio.
I probably messed it up.
Right? Maybe I'll do it this way.
Why not just do a direct comparison test?
I could have, but I just hadn't used this one yet.
Yeah.
It was suggested to me. So what if I factor out a 2 to the k top and bottom? Maybe that'll be easier to see what happens. Since 2 to the k is the pulling force on this guy. If I factor that out in the top, I get a k minus 1 here. If I factor it out on the bottom, then I get k over 2 to the k. How am I going to factor that out of the bottom? That's k 2 to the k plus 9k. So I'm going to get a k plus 9k over 2 to the k.
The 2Ks cancel.
I factored it out to cancel the 2k's and you can see what the limit's going to do. Because this one's bottom heavy, right? So that one's going to go to 0. That one doesn't go anywhere. So this behaves like 1 over 1. So I'm just getting a limit of 1. But it doesn't matter. I got a positive finite limit, so they both do the same thing. Both series behave the same way. So that one that I'm testing is going to follow the BK and converge. I do think a direct comparison would have worked as well. Maybe you have to worry about taking the limit. Because this one I made the numerators, this numerator is smaller than that one. This denominator is bigger than that one. So smaller over bigger becomes smaller. You could have done a direct comparison. Smaller than convergent is convergent. You wouldn't have to worry about that difficult limit. Somewhat difficult limit. Right? Direct comparison works just as quickly. All right, let's see what we did for number 6. K through, anybody do the K through test? the kth root of the general term, k plus 4 over 3k minus 1, which was to the k power. So the roots cancel, and we just take the limit of what's inside. And what's that limit? We compare it in size to 1, so it's smaller than 1. So it's convergent.
Absolutely.
Absolutely, because everything's positive to begin with. What you guys doing, number 7?
It's a telescopic series.
Okay, number 7 can be written as a telescoping series, so let's look. 7 is the sum from k is equal to 3 to infinity, 1 over 4 times k minus 1 over 4k plus 4. So the giveaway here is when you see that difference of terms that look a lot alike, then maybe that we analyze the sum of the first n terms. So consider Sn. So let's write out the first so many terms. It starts with k is 3. So when k is 3, I have a 1/12
Minus 1/16.
minus 1/16. The next term is k is 4
1/16 plus 120.
minus 120.
Yeah, that's what I meant to say, yes.
And then 1 over 20 minus 1 over 24 until I get out to the nth one, and I'd have 1 over 4n minus 1 over 4n n plus 4,
Yes.
if that is visible on here. That is. And so these guys in between alternate signs. Minus 1/16 cancels here. Minus 120 adds to 0 there. There's going to be one that adds to that. And the first one is going to be gone here. So we're left with a finite sum in closed form.
That equals 0.
If the sequence of partial sums can be written in the general formula, and if the sequence converges, then so does the series. So the sequence converges if it has a limit. This is the only term that has ends on it. They're on the bottom. So what happens to the limit here? That one goes to 0, leaves me with 1/12. And so my conclusion is that the sequence of partial sums converge to 1/12, so the series does as well. Sequence of partial sums converge, and so does the series. I guess we locked out, or what happened? I think so. Yeah. I unlocked it. All right, that was number 7. So far, so good? All right, let me rub this out. How many did you get a chance to try on that second page, the back page?
Forgot it existed, I'm not gonna lie.
A few.
So take a look at number 8 and tell me what you would try. Can't do the root test because that K downstairs doesn't have a K power. So try the ratio test while I rub this off.
Could we just
Try the
take a
ratio
limit?
test on number 8.
Take a limit of this one?
Are you sure what grows faster?
Doesn't 3 to the k go faster than 2 to the k?
You ever got multiplying it by K?
It's the 1/2, so.
Does that change it directly? I think you're right. I think we should get an infinite limit.
I don't think that affects it enough, right? Because if you keep going to infinity, eventually that won't matter.
What?
Or am I wrong?
I think you're right. I think you could argue with me and say that that has a limit. Right, divide everything by 3 to the K.
get
I just started first.
Yeah, I saw ratio test, but he suggested test for divergence. I think either one of them work. I'm gonna do the ratio test just to give us extra practice at it. But I think it's gonna diverge by the test for divergence. Oops, because that 2 to the k grows slower on the bottom. But ratio test will look like this. We're taking the limit as k goes to infinity. For the k plus first term over the kth term. So let's increase each k by 1. Then we'll have 3 to the k plus 1 over k plus 1 times 2 to the k plus 1. Then when we divide by that, the reciprocal gives me times k 2 to the k over 3 to the k. And so I'm going to rewrite that so I can see how it cancels. Right, that is 3 to the k times 3 to the 1. Then I have a k plus 1, 2 to the k, 2 to the 1. Pencil in another color, I have a better chance of seeing what's left. That one. And that one. So we have 3k divided by
2K plus 2,
yeah.
which equals 3 times.
So we were able to simplify that to 3k divided by 2k plus 2. When we take the limit of something that is the same power on top as on bottom, we just get the ratio of the coefficients. And it's the size of the limit that tells us what's happening.
Greater than 1.
Bigger than 1, so the ratio test says this thing diverges. Okay? What about number 9?
You could also do test for divergence
I
here.
think we'll do the test for divergence in number 9. Take the general term and run the limit on it.
I call it a divergence.
Because
I did the limit comparison test.
you compared it to 3 over 2 to the k, 3 to k over 2 to the k, that'll work as well. But this is the highest power on the bottom, this is the highest power on the top, and it looks top heavy. And so that limit is infinite. And so diverges by our test for divergence. What do you think about number 10?
Yeah, I was gonna try a direct comparison, but I don't think it worked.
The comparison doesn't work.
I think you can do a limit comparison. Try to do a limit comparison test. Make your comparison series the one that doesn't have the 2 on the bottom. Take away the -2. Simplify the BK series to a P series. Decide whether it converges or not. And then do the limit comparison test.
I was a +4.
Does
Yeah,
it?
does.
Oh, go ahead.
Top of.
So throw away the 4, throw away the 2, simplify that as a P series. And then do a limit comparison test with that known P series. You guys enjoy your extra hour of sleep this morning?
No.
It was more like yesterday morning.
Yesterday? Of course, my husband forgot to shut off his alarm, which normally goes off at 5 a.m.
I was still up.
You were not-
You were still up when it switched.
I was up.
Yeah.
I was up like, I would have been 30 minutes before.
No,
It pushed it
shut
to-
that.
I've never done daylight savings before. What?
Yeah, why were you up so late?
Why
Just
not?
say we're
We
not
did
doing
class
it.
quiz.
I thought I was gonna be late to class, or I thought I was late to class this morning, because normally when I walk to class, it's dark outside and I watch the sunrise, and I was like, the sun is out, I missed my whole class, but it was okay.
That's how I was.
Last year, I heard
We lost our attention span.
someone's trying to get.
Did you see how quickly that happened? Right in the middle of a limit comparison test.
It's Monday morning, 8 a.m., it's like 8:30.
Sure, I'm pretty sure.
Darby's.
We're gonna pick lookalike series first, just to have the square root of k over k squared. Squared is a 1/2 power. So 2 minus a half leaves me 3/2 on the bottom. That's my P series, 1 over k to the 3/2. Does that P series converge or diverge? Well, I heard both answers.
It converges.
P
Wait.
series converge when the powers are bigger than 1. If you can't remember that, integrate it real quickly, right? The integral of p to the negative 3/2 is going to converge.
I gotta confuse the geometry series.
I know, it's so easy to get mixed up because we're comparing things to 1, and sometimes equal to 1 is good, sometimes it's not good. You gotta have these series tests down. P is bigger than 1, so my BKs converge. Now I'm gonna do the limit comparison test. Where I take the limit of the given series over the BK series. And if I put it in there before I simplified, it's easy to see that I'm gonna have the same power, top and bottom. Right, if I just use my BK series like that,
They do the same thing.
so I should have a limit of 1. I do the same. And that means given series converges by the limit comparison test. Okay.
Is today Taylor series or tomorrow?
Oh, I will do power series today. Okay, number 11. Hopefully this one made you think of one that you did on your web work. You can do the K through test, but what will you get when you take the K through and then take the limit?
1.
And that says the test is inconclusive. So even though this has a K power out here, once you take the K through and take the limit, you just get 1. And the ratio and root test are inconclusive. So hopefully this problem made you think of that problem where you had that general term in a sequence and that general term in a series. And when you took the limit of it for the sequence, you got e to something. Right? So I'm thinking I'm going to get an e to the something in here, which isn't 0. So I'm going to do the test for divergence. But let's go through all of the formal steps of computing the limit. Let's try the test for divergence.
You could factor it k times.
And that would help me how?
Big brain.
Because in this form, it looks like 1 to the infinity, correct? So when you see something that has the form of 1 to infinity, you need to suspect e is going to play a role somewhere. And it's gonna be awfully hard to get e to a power to ever equal 0. Right? So you gotta suspect this isn't gonna converge. So let's see if you can do this. Let's see, you take it all the way down. Let me see if you guys can find out that you're gonna get something like e to the 7th power, maybe. A plus sign there or minus sign? It's a plus sign. See if you can compute that limit and get e to the 7th power. Let me know if you need some help. I want you to be able to do the stuff where you take the natural log of both sides, bring the power down, write it as 0 over 0, and then do L'Hopital's rule. But you know how to do all these steps because there's somebody in your dorm in Cal 1 that's going to want you to show them how to do it right. Good, you're doing L'Hopital's rule now. Yep. 1 over u prime. Right, the derivative logarithm.
Yes, deriving.
Derivative inside, did you do it that way?
Is negative seven.
You get it?
K to the -2.
Seven.
What was that?
Divergent.
Yep, what'd you get? For your limit?
Don't need to do the limit.
So that's
I
down
just
here.
think really hard about it.
Oh, really? And what did you think really hard?
It's divergent.
But how?
We 1 over u first.
Because
You're gonna go
okay.
1 over
So
that.
you have
She
a K
literally
power.
told us what the
One
answer
of this
was. Fun
doesn't-
fact.
this
Doesn't
Did she?
just
I was-
put that only because of the sum.
And she just said find
I
it.
take it 1 over the whole parentheses, the way you see it.
Well, because
There
you
you
have
go.
1
Now
plus
you're inside taking
something,
the
it's always a
derivative of
number.
those 2 terms.
And
So
K
what's the
power,
derivative
so
of
it's gonna be
7 over
divergent.
k?
You're always getting a bigger and bigger number.
Isn't it like the derivative of?
Yes,
7 times
but like we have to do it right above this, 3.3.
Yeah, so
Yes.
Well,
that'll
I'll
make
do
it.
I already turned it in, yeah, I
Give it
got
a-
100.
Okay. I think there's a pattern you can do in this one. So it might save time in the future.
Oh, yeah. I did it, I got you to the 7th, or fell out.
Yeah.
So, right, like.
I just, you know.
I really like that's gonna be the question on the test.
Most
No.
likely. But yeah, I'm pretty sure this is probably like.
Oh, got it?
You want
Yeah,
this
it's easy.
Should be
And
easy.
it's not really you do it,
Whatever you say.
How's it going? All right. I like to take, so we'll take the natural log both sides because it has a form of 1 to the infinity.
I'm hungry, but I'm not tired.
I
I
got
got so
tired.
much sleep this weekend.
Maybe I don't know if I'm tired, I'm just like not hungry.
Yeah.
That's really hard.
At the very least, you're always adding 1.
Stick you a natural log right there, and stick you a natural.
Definitely
log
tired.
there. Pull that K down to your power, and front of the log.
I just have the weirdest like impulse to like buy a coffee machine and drink black coffee every morning. I don't know where that came from.
You drink coffee normally?
Don't do it.
I know.
Do not recommend it. Doing it.
Jack, there's only one person who that could have
I
been.
know people
It could be Logan.
No, we couldn't.
Infinity
Why not?
times the log of 1.
Just-
Log of 1 is gonna be 0.
Every time
Logan, prove it
When
wrong.
that happens, we take this K. What is
See?
You gotta try.
Jack tapped me on the shoulder. Thinks he's being funny.
I was being cool.
Been messing with me all class. Like good
Jack,
shit.
you lost the funny
So
like
what's
a
this
week ago.
one?
Stop
Yeah.
trying.
No, that's why I was, I
His
got
hair's
the,
growing a little bit.
Yeah.
His hair's growing.
Yeah, I mean, it's
well,
Yeah.
you see,
slowly but surely.
Yeah.
I wonder if we can model your funniness of like
K
the.
is the same as pi.
Don't make me.
Now
do
it has the right form.
Just get like nose hair trimmers
Yeah, no,
and write
get
my
the-
name in my hair.
Give Jack a buzz cut.
Use a buddy.
Well, you see, your nails are made of keratin and so is your hair, so I bet it would work.
One time I was in like closet and I didn't want to wake up everybody going to get scissors, so I used nail polish to cut a tag off something.
Did it work?
Kind of.
I didn't have
It was
space
ugly.
on parentheses to take the derivative. I had all this.
So I did the one at the inside, a 7 plus.
I like the one for 7 over K there.
To start.
Yeah.
Outside here.
Well, you just think about it really hard and you can see divergence.
I can't do that.
Just
I
stare
don't
at
know.
Jack,
Well,
that's not gonna get you any right answers on the test.
No, this is obvious though. You're always adding one.
I know, it's obvious, but you have to work it out and do all the steps and do the formulas, or else she's not gonna give you any credit.
No, she won't give me partial credit if I'm wrong.
What?
She won't give me partial
No, she
credit.
doesn't- I don't think she doesn't give you partial credit if you like get it.
Does she?
Even if you get it right,
Did she give you
and
partial
you don't
credit?
get anything, and if you don't.
I just write
What if you just write the answer? Do you get partial credit?
No.
Big brain
Have you tried?
test.
But given like
The
the
big
emphasis she
brain
places on like the
test.
process, you're not
I'd
gonna
say
get full
it's-
points.
you
on
have
just
a
getting
big
right
brain.
answer.
Probably not full
Big
points,
brain
but
test.
you might get some points.
Well, you probably will get some points. What, you happy with the 50?
Yeah. It's worth like 2% of your grade.
No, it's test.
No, oh, you're talking about the test or the?
The
write-ups?
test.
Oh, we're talking about- I thought we were talking about write-ups.
No, I'm talking about the test. Jack is like, I just need to think really hard about it.
Well, this one you do.
Oh, wait, what, the test? I don't know.
This question is 100% gonna be on the test.
I think for the test, you don't need to show your grade, do you?
Yes, you do.
Well, you don't need to show.
For partial credit,
She
you
says
do.
you have to write out all your like tests.
If
and
you want
stuff like
partial
that,
credit,
otherwise
you
you won't
do.
give them credit. You won't get credit if you just write down 3 and 6.
I mean, I guess so. I don't know, I'm gonna do it anyway, because if I get it wrong, I still want partial credit. So I don't think it matters either way, unless you're being like Jack, not doing it, or
Like, I don't know how it's this, I definitely got this wrong.
didn't have to do anything.
I'm not sure if that's mathematically correct.
First one, I do.
It could be correct. Oh, yeah, you have to take that one. Okay.
Yeah,
Yeah.
go back and learn that.
The first chapter,
I didn't
The thing is, I still.
Yeah, you gotta take the
remember
limits.
The shells and.
Also, how could you tell by just staring at it?
Okay, it's really not. Okay, so here. 7 over K over here. 1 over 9. Is 7 divided by infinity 0.
All I got.
Well, so, but you'll still have that one.
What is this?
1 to the infinity.
Yes.
Well, no.
Well, it's bigger.
It's not, but it says not.
It's bigger. The true one, yeah, a true infinity, 1 to infinity, is 1. But it's not a true one, it's almost. It's a little bit bigger than
No,
1.
a true 1 to the infinity is indeterminate.
No, that's only with limits and stuff.
If you put 1 to the infinity, 1 to the n, and then opposed to the infinity, it is indeterminate.
Only if you approximate 1 and you approximate
It's harder to tell which
Which you have to do.
Yeah, but this way we know.
It's like either any
So you always add.
But it's just like whether or not you're
All right,
gonna.
let me do all the steps,
Add
just
that
because
infinity.
I like you. I'm gonna take, this has the form of 1 to the infinity,
Yeah.
so I'm gonna take the natural log of both sides.
It's easy to tell which one's the bigger. Okay.
And the K that's here then comes down here. But as K goes to infinity, that goes to infinity. 7 over K goes to 0, so the stuff in the parentheses is just 1. The natural log of 1 is 0. So we rearrange that. Take that K from front and put it underneath as a 1 over K. And so now I have it 0 over 0, and I use L'Hopital's rule. Where the log of something is 1 over that stuff. But then I have to go inside and take the derivative. The derivative of 1 is 0. 7 over K is that. So when I take the derivative, I get negative 7K to the negative 2. Downstairs, I got a K to the negative 1. So when I take the derivative of that, I get a minus K to the minus 2. Well, that's the natural log of L. So I have a K to the minus 2 on top. k to the minus 2 on the bottom. I'm going to cancel them. And I got a negative on the top and a negative on the bottom. I'm going to cancel those. Slide that 7 over here. And we've got the limit as k goes to infinity. Of 7 over 1 plus 7 over k. The only thing that has a k in it is this last term. So that's going to go to 0 and leaves us with 7. So L is e to the 7. And since that's not 0, series diverges.
So is the general form for 1 plus a constant over k to the, and then the whole thing to a k, just that number? E to that number?
Usually, depends, because I could stick, something changes if I put a number in here,
Okay, but as long as
if
it's
I put a
exactly
number
that.
there.
If the only thing we changed though is the 7.
If the
Yeah.
problem looks like that,
Yeah, but
that exact problem.
if I can put something here, here,
I mean,
and here, and I'm not sure, it's gonna be e to something.
Wouldn't you could just put the b in the numerator and have it like e to the 2/3 or whatever?
Maybe, I don't know the general rule, but that should give you some version of e.
Yeah, so it doesn't change that it diverges.
Right.
On the test, are we allowed to use the identity like 1 plus something over k to the k equals?
So
e
what
to-
if I throw all this baggage in there? You know what it's gonna be?
It's gonna be divergent,
Yes.
It's gonna be divergent, but.
as long as there's no negatives.
Oh, I could put a negative here.
Yeah, if that changes everything,
Ooh,
That's ugly.
maybe.
maybe, maybe not.
We will just give you.
So
an
just be
answer.
careful, just be careful. No, those steps are not difficult. All right, that takes care of number 11.
I literally saw you moving your hand.
There's several ways to do number 12. Somebody tell me how you did number 12.
I ran away from them.
12. Oh, I did 12. Oh, I did last time. I don't know what I did.
Know what you did?
Oh, I just did the integral test.
The integral test is what pops out to me.
I forgot about that.
Because I've got a u squared in the denominator and a du is the other term. So the integral test looks pretty good to me. You can also use a comparison test where you let the natural log of k be smaller than the square root of k.
Could you use the K through test on this one too?
No, because the k in the front. Right, you'll have a k to the 1 over k.
Oh, sorry, I was looking at 13.
Excuse me. Yeah, 13 is definitely a k through test. But I think I like the integral test on number 12, because we never get to use it, right? Spend all that stuff learning how to integrate, why not, what the heck, use it? So we're gonna let f of x be 3 over x, natural log of x squared. So since all of the x's are in the bottom, then it has to decrease, right? Because the numerator is constant. So f is decreasing and continuous on the interval from 2 to infinity. So we can integrate it from 2 to infinity. Where u is the stuff in the parentheses, and du gives us this 1 over x dx. So we're integrating 3u to the negative 2 du. Correct? Yeah, I got to that point. The integral of u to the minus 2 is done with the power rule. Add 1 to the power, divide by the new power. And so we get minus 3 u to the minus 1. So my antiderivative is minus 3 over u, which is the natural log of x. Then I have to evaluate that from 2 to n and let n go to infinity. So when I put an n in there, it's in the denominator. So that's good news. That makes it easy limit. When I subtract a minus, it gives me a plus. If the only n's in the denominator, what happens to the fraction? Goes to 0. So this first term is 0. The second term is a constant. And what's my conclusion?
Convergence.
The integral converges, so the series converges. Thirteen is the kth root test. This everything's to the kth power. If you kth root of that, you're left with a 3/2k. Then you take the limit. What's your conclusion?
Zero.
Zero.
And
I don't know what the.
It converges because it's less than one.
that's right. Kth root has the same conclusions as the ratio test. You take the limit of the k goes to infinity of the kth root of your general term. Since everybody has a k power, I can kill it. That limit is 0, compare in size to 1, limit smaller than 1 means the series converges. Everything's positive, so this is also absolute convergence. What are your thoughts on number 14? Disgusting?
I agree.
You're having disgusting thoughts?
Maybe a direct.
We would compare it. Do a comparison with the Q log series, right? As long as that 1 wasn't there, you got you a Q log.
Oh, yeah.
So we're going to compare to the series, and keep the 3, natural log of k over square root of k. This is a Q log series.
Q is greater or less, than,
Q is a half.
which is less than 1, so it diverges.
The 3 doesn't, the 3 is a constant.
So you could take it off.
Yeah, I could take it off if I want. It just makes it easier to compare size now.
Yeah.
How does the original series compare in size to this divergent Q log series? It's bigger because it's got 1 more constant inside the logarithm, right? So our series is bigger than a divergent series, and that is a good statement for the direct comparison test. We've got the direct comparison test, bigger than divergent is divergent.
Is there a single test that works every single time?
Nope. Otherwise, we would have been able to condense chapter 7 or 8 into one cute little section. Here, do this every single time. Just smell it. Ooh, that's divergent. So those of you that had that COVID smell problem.
Hey, that was me the first.
Auto filter.
Well,
I have it, but it's not COVID. There's no smoke.
you need it now, though.
First meal that I tasted after I drove.
So then we better have the test you can write down.
Yeah.
That smell test works for everything. What are your thoughts on number 15?
Ratio test.
Let's do a ratio test. We have a k power, we got a factorial. So 3 to the k divided by 2k plus 1 factorial. So if we're gonna do a ratio test, do you know how to handle 2k plus 1 factorial? How do I do the ak plus 1? Right, when you make the k plus first term here, you're changing each k to k plus 1. So your k plus first term will have a 2 times the quantity k plus 1, then a plus 1, then the factorial. Let's see how you take care of that.
Yeah, I had to go around.
Golly. Section 13.4 is gonna stay there. I can't get that, not very vertical
You want me
today.
to?
No, it's okay.
Okay.
I wonder who teachers in here beforehand, are they like 7 feet tall, like who would
It's
write
Dr.
them?
Elisa.
Oh, wait, is that
Large
the,
wingspan.
he's
The tall man.
he's the Calc 3 teacher.
Oh, is that why they're on 13.4?
Probably.
Yeah, that does make sense.
I didn't even think anything
I
of it.
didn't either.
I was like, oh yeah, 4. That's something that we've done.
So that's what I was saying about the K plus first term. Each K is replaced by K plus 1. Now I gotta divide by that. So this is 2K plus 3 factorial. So I need to know how I'm gonna be able to cancel.
So that would be 2K plus
3 times
2K plus 2
times 2K plus 1 factorial.
Perfect. So this is what I was told, that 2K plus 3 factorial. Start with 2K plus 3. Go down by 1 to 2K plus 2. Go down by 1 and you're at 2K plus 1, and now it matches. So you can put the factorial on there. This I can write as 3K times 3. And then I have my 2K plus 1 factorial. And then I have my 3K. And so we cancel here, here, here. So I got a 3 over a bunch of Ks.
I'm supposed to cancel.
3 over 2K plus 3 times 2K plus 2. But all the Ks are on the bottom. So that means our limit is 0. Do we have a conclusion when the limit is 0 at the ratio test?
Convergence was less than 1.
Less than 1 means it's convergent.
That makes sense.
Last one is an alternating series. So we got to test it for absolute convergence first. (16K) 0 to infinity of minus 1 to the K over 2 squared of K plus 3. So first check for absolute convergence. We can do absolute convergence with our ratio test and absolute value, or the root test and absolute value, both of which are bad for polynomial type terms. So we're just going to take the absolute value. And you're going to tell me what you know about the absolute value series.
It's like a compared to a P series.
Yeah. And then,
Looks like it's going to diverge, doesn't it?
yeah.
This is going to diverge in limit comparison test to 1 over square root of K. Is a half divergent. Right? If I do the limit comparison test, I'll get a limit of a half, both do the same. So that means it's not absolutely convergent. So we got to check for conditional convergence. How? Alternating series test. That's our Texas 2-step. Right? Has to do 2 things. Does the limit go to 0 of the non-alternating part? And compare the size of the K plus 1 to the K. Does it decrease? Now tell me what the limit is here. It is 0. And I know that 2 square root of K plus 1 plus 3 is bigger than 2 square root of K plus 3. So the reciprocals go the other way. So it is decreasing. Right, if there's just a constant in the numerator, this is the easiest way to show decreasing. If I have k terms in the numerator and denominator, maybe it's easier to take the derivative to show it's decreasing. So it does both of the parts. That means it is conditionally convergent.
So we really have to worry about like absolutely convergent, conditionally convergent for these alternating ones, right? And like
Right.
for the rest of
Or
them.
anything that has negative terms in it. Right? Okay, so are you feeling any better about your test? You got a better idea of what's in your head about what's what?
I need to study.
You don't think it's
Yeah. Pretty good. Look at this last one.
Then add one together.
Okay, I'm going to give you a brief introduction to power series.
It sounds like a TV show I would watch as a kid.
You got the pink power series and the yellow power series.
Suddenly I'm more excited to learn about this.
And we have graphics to go along.
Show about that.
Yeah.
That one's-
Go up and draw some pictures on the board next to the power series.
But I'm not an artist of any regard.
All right.
See my Thomas the Tank Engine.
It was so bad.
I think we should be doing that on recording.
I'm gonna find it now.
Okay. So this is the beginning of section 8.7. Here's an example of a power series. Well, shoot, that's still power series. That's a polynomial. Power series is an infinite polynomial.
Okay, wait. My brain's thinking. Yeah, it is. That's what I was gonna say, something to the K power.
That's right. This particular infinite polynomial is a polynomial centered at x is equal to 0. Because I just have x to a power. If I want to shift it to the right c units, then I would write x minus c to a power.
So a power series is just a
Polynomial.
alternating series
Power series is a polynomial,
with.
doesn't necessarily alternate.
Sounds like a geometric series of extra steps.
There we go.
It could alternate. But it's an infinite polynomial centered at x is equal to c. What do graphs of polynomials typically look like? Right, x to the first power, x squared, x cubed, got some wiggles in it maybe. So those coefficients, A0, A1, A2 are called the coefficients. So these are the coefficients of the powers on the K. Coefficients are going to stretch it out a little bit, maybe flatten it out a bit. But these power series are polynomials that are generally smooth. In calculus, smooth is good. Smooth means it has a derivative everywhere, right? And antiderivatives, things like that. With a polynomial, you can take the derivative term by term. You can take the antiderivative term by term. If I want to find the value of the polynomial at x is 2, I put in a 2 for each x. It's easy arithmetic, right? Exponents are whole numbers. What we're going to do with these polynomials is for different things here, they behave in a different way. They will converge on some interval. The interval might be a portion of the real number line, either a closed interval or half open, half closed, or an open interval. They might converge over the entire number line, or they might converge only for a single point. X is equal to C. So a power series has an interval of convergence and the interval might be something like that, or that, or that, or that. Open, closed, or half open, closed. It might be a whole number line, or it might be just a single point. It's going to have one of these conditions. Our job is going to be able to find what is the interval of convergence. And then once we get the hang of that, we're going to find out, okay, what does it converge to? We're going to find that we can build these polynomials so that they'll converge to things like e to the x, or the sine of x, or the tangent of x. We already know a power series for this particular polynomial. 1 minute, this is an exciting one because we already know one.
Is it the one that was assigned?
I don't know what was assigned.
Oh, that was assigned,
This is,
not yet.
okay,
That's supposed to look like a cosine.
right? This is a polynomial where all of the a, k's over there are just ones. But do you recognize this particular pattern? I get from one term to the next just by multiplying by x. What kind of series do we have where you get from one term to the other by multiplying?
Ratio test.
This is a geometric series
Ratio test.
in which r is equal to x. So for what values of r will the geometric series converge? So there's our interval of convergence. It's the open interval from -1 to 1. And what does this particular power series converge to? On this interval, it converges to a over 1 minus r. A over 1 minus x. Right? Here's a rational function that has a discontinuity when x is 1. Not to worry, it's not in the interval of convergence. If you were to graph this, it looks like those hyperbolas, right? With a vertical asymptote at x is 1. On the interval from -1 to 1, it looks exactly like, this polynomial looks just like that. So if I went to say Mathematica and say graph this guy, its graph will look like that graph exactly right in here between -1 and 1. Lays right on top of it. Outside it does weird things, but in that interval it meets it perfectly. Okay? Good. We're going to use the ratio test and the root test to find these intervals of convergence. That's right. I get homework, very good. Yes.
Want to take a calculator?
Sorry.
How dare you? You stole from me first, all right? You had it coming.
No, I stole a pencil and gave it back to you. I was just thinking.
Yeah.
You pranked me.
And
There,
I have a problem with that. You have a problem with that?
Yeah, I have a problem with that.
What are you gonna do about it?
I have a nice.
That is really
ethics
good.
project that I have.
I'm so jealous of your talent.
Yeah, so I have a question about. So.
No catfighting?
No, we're man fighting.
Come on, man fight. Best of three, best of three.
No,
No,
that's what losers say.
No, best of three.
So this one is going to be absolutely convergent.
Is it though?
Because in absolute value, you can.
It's not always decreasing. I want the pasta.
It decreases far enough down the
You wanna
line.
go, well, yes, Fazoli's where Paul is not right now, or is it?
I'm gonna probably go get some.
Yeah,
Okay, I'll see you in a little.
No, it has to decrease in the long run. That has to say alternates. Decreases in the long run.
Things, the limit,
Limit goes to zero and it decreases in the long run.
but isn't that just? if
Yeah,
limit
but
equals
that's
zero,
gonna-
it is gonna decrease?
Not always. But this
Okay.
one, if you put it in absolute value bars, you can compare it to 5n over n cubed, which behaves like a convergent P series,
But it actually increases from n equals 1 to n equals 2.
but that doesn't matter.
It goes from negative.
But once you go beyond that, when then it's a big enough number, it's
I
decreasing.
thought every single term had to
Nope,
be.
doesn't have to, just in the long run.
Okay. Thank you. And so 8.6 doesn't have any write-ups?
I haven't put them up there yet,
Okay,
but I will.
okay,
I'd probably say problem number 1. Well, 3 parts.
thank you.
I'll put them up there when I get up to my office.